So next one, we can also use the inverse, the matrix inverse, to find the solution, because AX equals B, right? X should be, you know, X should be A inverse B. And then what is A inverse? We know X equals, for algebraic operation, there should be B over A. But in matrix, I cannot write it down the matrix like this. So I need to use A inverse. Okay. So how do I find the A inverse? And do we have some rules or properties for the inverse matrix? First, let's see. How do I know that B is an inverse of A? If I have two matrices, A and B, if A times B or even B times A is an identity matrix, then we say B is an inverse of A, or A is an inverse of B. So, because of this definition, non-singular means that a matrix if we say that this matrix is a non-singular, that means the matrix has an inverse. And exactly one inverse. Because let's prove that. Suppose we have two rather than one. B and C, they are inverse of the matrix A. Then what does that mean, inverse? B matrix, we can think about B matrix is B times the identity matrix n by n. What is identity matrix? That's A times C. Because C is an inverse of A, so AC or even CA should be identity matrix. So that's why I can change that, replace for AC. Then we can take the product first, BA n times C. And since we assume that B is an inverse of A, so when they have a product, it should be an identity matrix. And identity matrix times a matrix, there will be that matrix itself. So that's why B equals C. So B and C are the same. The non-singular matrix has exactly just one inverse. All right. Now let's see some properties. Identity matrix is non-singular. So, and also the inverse of the inverse of the identity matrix is the identity matrix itself. They won't change. The inverse of an inverse will become the matrix itself. Again, if the matrix A is non-singular. And how about I do the transpose and the inverse? I can also switch the order. I can have inverse first and do the transpose. A and B are non-singular. So A times B is also non-singular. And the inverse of A times B is also non-singular. And AB, the inverse, will be B inverse times A inverse. That's very important. It is not A times B. A inverse times B inverse. No. It'll be B inverse first and then A inverse. If one of them is singular, then A times B or B times A is also singular. Now, AX equals B. I can say A times A inverse will be A inverse B. Right? I times A inverse. And here, identity matrix X equals A inverse B. Identity matrix times X is X. So X equals A inverse B. Okay. Now I want to find the A inverse. Then I times B, I find the solution. So here is the method for finding the inverse of the matrix. If I have matrix A, how can I find the inverse? We can use identity matrix. First, let's have identity matrix and matrix A together to form an augmented matrix. So this is 1 0 0 1 5 6 minus 1 8. Now I want this becomes an identity matrix, and in that case this will be A inverse. So I would like to make A to be an identity matrix. In that case, first, the first row I can times 1/5. So this element will become 1. 1/5 0 0 1. 1 6 1/5 8. Now I want to create the leading entry, so I don't want this 6. So I will times minus 6 of the first row to the second row times minus 6. Then you get 1/5 0 minus 6 over 5 1. Then you have 1 0 minus 1/5 46 over 5. Now you want to change that to 1. So you times the second row, you times 5 over 46. And then you get 1/5 minus 6 over 46, 0, 5 over 46, and 2 more steps. Here you have 1 0 minus 1/5 and 1. Last one, you'll make the minus 1/5 this element to 0, so you times 1/5 of the second row to the first row. Then you get 8 over 46, 1 over 46. And here you have 1 0 0 1. You get identity on the right. So the A inverse will be 1 over 46, 8 minus 6, 1, 5. Okay. 5x equals 7. We know x is equal to 7 over 5. Right. That's quite easy. Now we will change that to a matrix. And also that we know that the denominator is not 0. If it's 0x equals 8, I cannot say that x is 8 over 0 because 0 in the denominator, there will be infinity. Okay, so ax equals b. Now think about the matrix. Ax equals b. I have a solution. I have a solution if and only if this A is non-singular. In like one equation that this coefficient should not be 0. And A is not singular means that I can write an inverse of A. I can have A inverse. So the unique solution is x equals A inverse B. 5x equals 7, x equals 5 inverse times 7. Right. I have inverse. 0 inverse, I don't know what it is. 0 inverse will be 1 over 0. So if I have a solution, then this solution is unique and I can express A inverse times B. If and only if A is non-singular. Okay. And let's jump to the other way to think that Ax equals 0. I have a non-trivial solution. Non-trivial solution means that x is not just 0 because x equals 0, I can say that x is 0, that's a solution, right? Then x is a trivial solution. But for non-trivial solution, x is not x is not a 0 vector. Then if and only if A is singular. What does that mean, non-singular and singular? Singular means that I cannot have an inverse. That means one of my rows or even columns, there will be all zeros. If one of my rows is all zeros, then times x1, x2, x3, x4. And it should be 0, still 0. Then my x is not just 0, right? Because 0x1 plus 0x2 plus 0x3 plus 0x4 equals 0. x1 could be 3, 4, whatever. x2 could be 5, 7. x3, x4, they could be non-zero. Then I have a non-trivial solution. Okay, so in this case, my A is singular. To have a non-trivial solution for Ax equals 0, then A should be singular. If it is non-singular, non-singular means that I have inverse. If I have inverse, x equals A inverse 0, then this is 0, so x should be 0. Then if x is a 0 vector, then x is a trivial solution. For non-trivial solution means I have a values for x. Okay, it's not just all zeros. Okay. Any questions for this one? So next, we're going to talk about the determinant, because we will also use determinant to express the solution of the system equations, or later on, the differential equations. So what is a determinant? I have a matrix A 2 by 2. Determinant A and I write it a bar included. For this A, there will be A times D, the elements A times D minus B times C. Okay, at least you need to remember this. AD minus BC. That is for the matrix 2 by 2. If it is 3 by 3 or like n by n, then I need to do the deduction 2 by 2, because we know the definition 2 by 2, that will be AD minus BC. So if I have a 3 by 3 matrix, then I will try to reduce that to 2 by 2. And how? Here, normally we can choose the first row. Okay, choose the first row. You can see my first 3 elements. And then if I choose the first element, then they will corresponding to the rest here. And then do the determinant. If I choose 8, 1, 2, then I will do this determinant, the rest. So cross out their corresponding row and column. The rest will be in your determinant. And since 1 plus 2 is 3, that's odd. If it is odd, then I need minus sign. If it is even, 1 plus 1 equals 2. That's even, I don't need the minus sign. Here, 1 plus 3, that's 4. Even number, no negative sign. For 1, 3, choose 1, 3, and cross out their corresponding column and a row. Then the rest part will be in your determinant. Okay? Then what is this determinant? Or this matrix, and then we take the determinant. This is called cofactors of Aij. Cofactors of Aij, A1, 1, for example. Then we say this is Cij. Same subscript. How do I define this C? Minus 1 to the I plus j. This is to determine that if we have negative sign or not. If I plus j is an even number, minus 1 to the 4th, minus 1 to the 2, that will be 1. So that's why that we don't have minus sign. Minus 1 to the 1 plus 2, it is 3. So there'll be minus 1. That's why we have minus sign here. Okay. And then to determine the minus 1 and 1 later on, we need this m, ij. And we call this m, ij. Mij is a minor determinant. Minor determinant is like here. A smaller one will be the 2 by 2 in this case. Or here, the rest. And we will say that Cij will be equal to the minor determinant if I plus j is even. Otherwise, I have a negative sign, m minus Mij. If I plus j is odd. So here this is C11, C12, C13. Let's just see this example. Then you will know that how to find the determinant. Now I have 3 by 3 rather than 2 by 2. Oh yeah, 3 by 3. For 3 by 3, you choose the first row. Okay, the first row, your determinant I have 2. If I choose the first element, cross out the corresponding row and column, then the rest will be your minor determinant. Okay. There'll be C11. And then the second element 4. I choose 4, then I cross out their corresponding row and column. Then I have 6133 as my minor determinant C12. And 7, cross out the row, column. This will be my minor determinant C13. C11. Minus 1. Here is 1 plus 1. And cross all this. So you have determinant 0533. And C12. Minus 1, 1 plus 2. C12, 4, so I got 6133. So 6133. And C13 minus 1, 1 plus 3, 6105. And finally you'll get the determinant is 120. Alright. How do you find this determinant? 0 times 3 minus 5 times 3, so it'll be minus 15. 18 minus 3, 15. 30 minus 0. Okay. And sometimes you may see that those elements, the numbers are nasty. So we can simplify that to find the determinant. So here let's learn some properties of the determinants. So I have 2 matrices and they are n by n. First, if B is formed from A by interchanging 2 rows or 2 columns, then the determinant of B will be equal to determinant of A with a minus sign. So like 1, 1, 3, 5, 2, 0, 4, 3, 4, 5. And if I change 2 rows, 204, 1, 3, 5, 3, 4, 5. I change the first one and the second row, then I should have a minus sign. Easier way, 1, 0, 1, 0, 0, 1. The determinant is 1, right? Then if I switch 2 rows, you get -1. So if you interchange two rows or two columns, then you will change the sign. If you change one time, you change the sign. You change the second time, then you change the sign again. If B is formed from A by multiplying any row or column of A by a scalar of alpha, then the determinant B will be alpha times determinant A. The easy one. A is 1. Determinant of A is 1, 0, 0, 1. And then B will be 3, 0, 0, 3. No, just 3, 0, 0, 1. Okay, I times 3 to row 1. Multiplying the first row of A by 3. Then you get 3. This one is 1. So it's 3 times A. 3 times the determinant of A. Okay? If A has a 0 row or column, then the determinant of A you don't need to calculate. That's 0. Easier, because if I have matrix 0, 0, 0, 1, 2, 3, 4, 5, 6, remember that how do we find a determinant using deduction? Choose the first row, 0 times the minor determinant, 0 times minor determinant, 0 times minor determinant, they are all zeros. Once you have a row of 0, then your determinant is 0 right away. Okay? If you have two identical rows or even columns, then your determinant is also 0. 1, 1, 1, 1. 1 minus 1, that's 0. If one row of A is a constant multiplier of another row, this row is a constant multiple of the other row. This one is like the first row times 1. Then the determinant is 0. If you have 1, 1, 3, 3. The second row is a constant multiple of another row for the first row by 3. Then the determinant is still 0. Last one, if matrix B is formed from A, and this time they add a constant multiple of one row to another row, then the determinant of B is equal to the determinant of A. If I just do the row or even the column, the row operations, then their determinant should be the same. For example, this determinant is minus 83. If I have the second row times minus 3 and then add it to the third row, then the determinant should be the same. So 4 minus 2, 1, 3, 0, 5. And here if I times minus 3 from the second row, then added to the third row. Then the determinant is still minus 83. Think about this identity matrix 1 0 0 1. The determinant is 1. If I times 2 of the first row and add it to the second row, then I'll get 2 1, right? Then the determinant is still 1, right? Because here their multiplication is 0, it's still 1. So if you do any like row operations, the determinant is the same. Okay, any questions for this one so far? If I transpose the matrix, the determinant is the same. 1 0 0 1. Then the transpose is still 1 0 0 1, and then the determinant is the same. If I have a valid product for those two matrices, then the determinant, I can find the determinant for each and then times together. And then we can use determinant to find the inverse matrix. This is another way to find the inverse matrix. A is n by n, non-singular. Non-singular, again, that you won't expect to see 0 rows or 0 vectors in your matrix. That's a non-singular matrix. Then B inverse, B is the inverse matrix of A. That means the element B ij should be 1 over determinant of A, and then minus 1 I plus j with a minor determinant. This m, not ij, there will be ji. And then the ij transpose is ji. Let's just use this example to find the A inverse. First, we need to know the determinant. So for A inverse, we need to find the determinant first. The determinant is minus 18. Now we want to find B11. This is B11, 12, 13, B21, B31, B33. Okay, first element, there will be 1 over minus 18. That's determinant of A. Okay, minus 1 and 1, 1 means 1 plus 1. So even number. So that also means if you are in the even element, there'll be 1. You don't need to change the sign. So I choose this because 1, 1 is still here. Then I cross out their corresponding row and vector. So I get minus 2, 4, and 1, 0. Minus 2, 4, 1, 0. B12. 1 over the determinant of A minus 1, 1 plus 2. So now you see here is minus 1. And the m, here is 2, 1. What does 2, 1 means? First, I want to find this value, b1, 2. But I need to use the minor determinant 2, 1. So their diagonal, their corresponding, the opposite one here. 2, 1, and then cross out their corresponding row and the vector. Then you have 0, 4, and 1, 0. Zero, 4, 1, 0. You get minus 4 over 18. B1, 3, 1 over the determinant of A, minus 1, 1 plus 3, so it's 1. And here we need to switch. 1, 3 becomes 3, 1. So I want this value. How can I get this element? They're corresponding the opposite position here, 3, 1. So cross out the row and the column. Cross out the row and column, we get 0, minus 2, 1, 1. That's minus 2 over 18. And finally, you'll get A inverse. Take 1 over 18 outside. So far, we found 4, minus 4, and minus 2. And your time to find the rest. So what are the rest? B21, B22, B23, B31, B32, B33. Okay, let me give you 5 minutes. Right, so how about this element? What is the value for A or B21? Yes. How much? For this one? Yeah. Minus 1. Good. 1. And this one here? Minus 5. It should be 5. So here we have minus 1, 1, and 5. Okay, so let's see for here. If I want to find this B23, I want to find B23, then I will jump to here, 3, 2, and cross out. And then I get 1, 8, 3, 1. So it should be 5. Let me see. And then it should be minus 5. How about the third row? I want to find this element. That means I'll jump to here. 1, 3. Cross out. So 12 minus minus 2, 14. So here should be 14. Right. Let me see. Because I put, oh, sorry. I only take 1 over 18 outside. it should be 1 over minus 18. Okay, and then it should be, well, to find the element, then yes, that will be minus 5. But I put a negative already, so here's 5, minus 14. Find this one, so go to here, this part. There'll be 32. And then 16. Okay. Well, it's better that you put the minus here. Okay, put minus outside, so there will be 1 over your determinant A. And then you will change all the signs. All right. Any questions for this one? Now, if you don't have any questions, then we can use the determinant to solve the system equations. It is called the Cramer's rule. So using the determinant to solve systems, I have n linear equations and also n variables. So x1 to xn. Now, A is a coefficient matrix. Okay, A is, because this one I can write down AX equals B. And then if determinant A is not 0, then I can use the Cramer's rule, and the solution is determinant A1 divided by determinant A, x2 determinant A2 by determinant A, to xn determinant AN divided by determinant A. And here, what is determinant A1, A2 to AN? If I have a matrix called AK, that means I just replace the kth column by B. So here should be A1K, A2K to ANK. But now I just change that, replace that by B1 to Bn. Okay, then that is your solution. Let's use this example, then they'll be clear. This system, I can get the x1 right away. x1. The denominator is the determinant A. So determinant A is A11, A21, A12, A22. Then how about the numerator? It's x1. So my first column will be replaced by B vector. So here, instead of A11, A21, there'll be B1, B2, and the rest same. A12, A22. For x2, the solution will be, denominator is the same, the determinant of A. And the numerator, since it's x2, so the second column will be replaced by B1, B2. Okay? Any questions for this? Let's see this example now. Try to find the real answer. For this system, 3 by 3, first we need to find the determinant of A. Determinant of A, the coefficient 3, 1, 5, 2 minus 1, 4, 1, 3 minus 2. Alright, let's find the determinant again. We can choose the first row 3 times the corresponding minor determinant minus 1, 4, 3 minus 2. Minus 2. Now for 2, cross out the corresponding row and column. I got 1, 5 and 3 minus 2. So 1, 5, 3 minus 2. And then the third one, 1. 1, 5 minus 1, 4. Now for x1, then we need the determinant a1. So determinant a1 A1 means the first column I will replace B to the first column. So the B is 7, 3, 1. And the rest will be the same. Determinant A2 in the second column. I will substitute B vector 7, 3, 1 to the second column. And the determinant A3, 3, 1, 5, 2 minus 1, 4. And then the third column will be vector B. Okay, please find these three determinants. If you find the answer, just shout it out. Say that determinant A1 is, or determinant A2 is. What is determinant A1? Minus 3, 9. A2? You can also use the properties of the determinants. That means that you can also do the Gauss-Jordan deduction method, because once you can get like only one, you only have a leading entry with 1 and also 0, 1 or something, that'll be easier. You choose the first row, easier to find, right? Because this is 0 and here probably also 0. A2, 38, 78, and A3, how much? 52. So then you can get your x1, x2, and x3. Okay? Any questions? Explain more about what? The Gaussian? Yep. Because for the property, you see the properties. The last one. Adding a constant multiple of one row to another row, the determinant is the same. Okay, so using this one back to here, for example, for this one, 3, 2, 7, 1, minus 1, 3, 5, 4, 1. So I can 1 minus 1, 3, and this will be 0. I times minus 3 of the second row to the first row, and then times minus 3, so there'll be 3. Here will be 5, right? Times minus 3, minus 9, plus 7, minus 2. Here I have a 0. Times minus 5, here will be 0. Minus 5, 9. Minus 5, minus 14. Right? Now, again, I will write it down here. 1 minus 1, 3. And then, no, since, for example, to here, you can still simplify that. But now I can choose this. If I choose this row, okay, now I have a 0. So 0 times anything, 0. So you only need to do like 2 determinants, right? 5 with their corresponding, the minor determinant, and minus 2. You can also like times 1/5 times 1/5 to the second row, and then finally you'll get like 1 something, like 0. And here I have, just try to make more zeros. Then you don't need to calculate like every determinant, especially for like this. For like 4 by 4, 5 by 5, yeah, you can choose the first row. Okay, this one with like still 3 by 3, and for this 3 by 3, you need to also choose the first row and do that again. But if you can simplify this matrix first, simplify it to like, suppose, for example, like 0, 1, 3, 2, 1, 0, 3, 2, 0, 1, and 0, 5, and 0, 0, 1, 3. Oh, then here should be 0, 1, 2, 3, 4, and 0, 0, 0, 1. Then if you choose this, you only need to do like a two times of your determinant, rather than, well, you choose like so many like nasty numbers. Okay, right? Because their determinant should be the same. You can also interchange 2 rows, but remember that every time when you change 2 rows, then you have a negative sign. If you change 2 rows 2 times, then minus sign times minus sign, that'll be positive. Okay, so if you change these 2 rows, and then this one and this one, I also change that, then their determinant should be the same, because you change rows 2 times. Or you try to get, using this property, you try to get a 0 row, then your determinant is 0. Okay. So till here, on Wednesday, your midterm from power series to Cramer's rule. Okay, and you'll try to find the solution of an equation using different methods, like the Cramer's rule. You can also use the inverse matrix to find the solution. Use the Gauss-Jordan method to find the solution. You need to know how to use different methods to find the system equations, the solution of the system's equations. Okay. Next, we will talk about the eigenvalues and the eigenvectors. And this one, I think there will be a brand new concept for you to learn. And it is like a magic. Okay. And you will use eigenvalues and eigenvectors a lot in many different applications. So one of your homeworks questions could be this. You can investigate which kind of problems that will use eigenvalues and eigenvectors. There'll be a lot. Okay. And then what is eigenvalues and eigenvectors? First, say A is n by n matrix. Real numbers or complex numbers, doesn't matter, just n by n. And we say that I have a real or complex number of lambda. This is called eigenvalue of matrix A. If and only if I have non-zero n by 1 vector x such that ax equals lambda x, then x is called eigenvector. Lambda is called eigenvalue. You can see that ax, I have matrix times a vector. And then finally, I can express this matrix times a vector as a scalar, lambda times a vector. Finally, this is a vector. And here it is also a vector. This is n by n, x is n by 1. So here's n by 1, n by 1. So you see that from the matrix to a scalar x, scalar lambda. If you satisfy this, then we call that lambda is an eigenvalue, and x is called eigenvector of the matrix A. Don't you think it's like a magic? Like my matrix now becomes a scalar to express the same thing. First, zero vector cannot be an eigenvector. Eigenvector is x, so x cannot be a zero vector. Otherwise, a times 0, there'll be always something times 0. Right? 0 cannot be the eigenvector. But 0 can be the eigenvalue. Lambda could be 0. But 0 cannot be x. Zero vector cannot be x. For example, here I have A matrix A times a vector x. This is 0. Okay. A times x is 0. So I can also think about like 0 as a lambda times this x. 0 is an eigenvector. 0 is an eigenvalue. And then x 04 is an eigenvector. Let's see this equation. Ax equals lambda x. So Ax, put it to the left side, lambda x equals 0. Here 0 is a 0 vector, okay, it's not just a scalar 0. So you could rearrange that A minus lambda I identity matrix x is a 0 vector. In the beginning of the class today, we say that Ax equals 0. To find a non-trivial solution, this matrix should be singular. So this matrix should be singular. And this is the homogeneous system. of n linear equations in n unknowns. So as I said that for this system, I have a non-trivial solution because trivial solution apparently x is all 0. So non-trivial solution if and only if the determinant of a minus lambda I is 0 because a minus lambda I is singular. Very important. This will be your characteristic equation. Lambda is an eigenvalue of A if the determinant is 0. This is called characteristic equation. And then if lambda is an eigenvalue of A, then any non-trivial solution, this solution is the corresponding eigenvector. The solution is x, right? And this corresponding x will be, this x will be the corresponding eigenvector. One eigenvalue, I will have one eigenvector. Okay. For example, if I have a matrix A 2 by 2, then we want to find the eigenvalue and eigenvector so that this matrix A times your eigenvector, I can use eigenvalue times eigenvector. First, we need to check their characteristic equation, because if I have an eigenvalue, then if and only if the determinant of A minus lambda I should be 0. So A minus lambda I is 2 minus lambda 1, 2, 3 minus lambda. Let's find the determinant A minus lambda I. You will take the determinant, this times this, minus 2 times 1. We get lambda minus 1 and lambda minus 4. We also call this as a characteristic polynomial. So when this equals 0, what do I have? Lambda could be 1 and 4. Right. So when lambda is 1, that is the eigenvalue, and then I should have a corresponding eigenvector x. When lambda equals 4, I also have a corresponding eigenvector x. They are different. So first, when lambda equals 1, A minus lambda I will be 1, 1, 2, 2. So this times x should be 0, is a zero vector, then your x, we will learn how to find this x. But x here you can see -2, 1. This is your eigenvector. When lambda is 4, I have -2, 1, 2, -1. To satisfy this bigger A times x equals 0, then we have 1, 1 as our eigenvector. Okay. Next, let's see the matrix 3 by 3. First, to find the eigenvalue, eigenvector, we need to find the determinant of A minus lambda I. This is 3 by 3, so 1 minus lambda, 0, 0, minus 1, 1 minus lambda, 0, 0, 1, minus 1 minus lambda. Lambda minus 1 squared. Lambda plus 1. That's 0. So you will get lambda equals 1, 1, minus 1. So I have two eigenvalues, then I should have two different eigenvectors. When lambda equals 1, your A minus lambda I will be 0, 0, 0, minus 1, 0, 0, 0, 1, minus 2. x1, x2, x3. That should be equal to 0 vector. Then you can find the eigenvector should be 1, 0, 0. That will satisfy this equation. When lambda is minus 1, I have 2, 0, 0, minus 1, 2, 0, 0, 1, 0. Times the x. It should be a 0 vector. Then in this case, my eigenvector is 1, 2, minus 4. As long as they satisfy this equation, okay, you can get 2, 4, minus 8. That's okay. Any questions so far? No, then how about 2 by 2 this time? Every time we need to find the determinant of A minus lambda I. This identity matrix I depends on your matrix A. The size of matrix I depends on your matrix A. Okay, if A is 2 by 2, then my identity matrix is 2 by 2. If it is 3 by 3 for the matrix A, then the identity matrix should be 3 by 3. 1 minus lambda, 2 minus 2, and minus lambda. I got lambda squared minus lambda plus 4 equals 0. And then you get your lambda is a complex number. 1 plus minus square root of 15 times I divided by 2. So even it is a complex number, we still have two roots, two distinct eigenvalues. For the distinct eigenvalues, I have their corresponding eigenvectors. So first, let's consider the plus sign, 1 plus square root of 15i divided by 2. Now, a minus lambda I times the x should be 0. 1 minus 1 plus square root of 15i divided by 2. 2 minus 2, and here's minus 1 plus square root of 15i divided by 2. This x1, x2. Okay, so here should be 0. Then your x2 should be 1 minus square root of 15i divided by 2 times x1. So I can choose x1 is 1, your eigenvector 1 minus square root of 15 times I divided by 2. And later on you will learn since your eigenvalues are complex, then your eigenvectors should be conjugate. You can also do the same thing then, but I can predict that your eigenvector conjugate. So 1, this is 1 minus 15, square root of 15, so here should be plus square root of 15. Right, so for those three examples, you can see that your eigenvalues could be just a real number or a repeated roots, and even the complex numbers. And as long as you have eigenvalues, then you should find the corresponding eigenvector. Here's a note. If alpha is a non-zero scalar and x is the eigenvector with the eigenvalue lambda, then at times alpha, then the eigenvalue is still lambda. Just like here, I said that you can choose 1, 0, 0 or 2, 0, 0 or 4, 0, 0, 4, 0, 0. It's just like alpha times 1, 0, 0. They have the same eigenvalue. So here, multiple of an eigenvector is an eigenvector. You can see that A now rather than x is alpha x. Let's see. Alpha x, since alpha is a scalar, so I can put alpha outside. I times A x, right? And then since lambda is an eigenvalue, so ax becomes lambda x. And then we put the scalar back, lambda times alpha x. All right. Next, if I have a m eigenvectors, and for these m eigenvectors, I have their corresponding eigenvalues, lambda 1 to lambda m. And for lambda 1 to lambda m, they are distinct. Okay, they are not the same. Then the eigenvectors is linearly independent. x1, x2, 2, xm is linearly independent. Alright, so who can tell me that? What does that mean? Linearly independent. If we say that those vectors are linearly independent, what does that mean? What does that mean that they are linearly independent? x1 to xm. Yeah, so one of their vector cannot be expressed as a linear combination of the rest. So they are linearly independent. Here's a note. A n by n, I can have at most n eigenvectors with distinct eigenvalues because it's only n by n. For example, I have a 3 by 3. I can have at most 3 eigenvalues or eigenvectors. I cannot have 4. Okay, because if you see the characteristic equations, if you find the determinant minus lambda I, then finally the characteristic polynomials, the order is 3. So you can get at most 3 distinct eigenvalues. You cannot have more. And each eigenvalue I can get an eigenvector. So I have at most n eigenvectors. Okay. And before we dismiss the class, let's see one of the applications, small applications for learning eigenvalues and eigenvectors. It is just try to find the power of matrix. I have a power of matrix a to the m. So I times a m times. But how do we calculate a to the m? If I have a 1, 3, 5 minus 2 to 2024, I cannot just do it by hands, right? Like this times another matrix times another matrix. It is inefficient. So to find this power of matrix, we can use the Cayley-Hamilton theory. Matrix A n by n satisfies its own characteristic equation, which means a minus lambda I, the determinant will be the equals 0. That will be the characteristic equation. Then if this polynomial is the characteristic equation of A, then you can just change this eigenvalue lambda to the matrix A. They are the same. I have a characteristic equations here, and then I can change that to a squared minus a plus 4 is 0. That's also correct. Didn't change that. It should be 0 vector. Okay. So, for example, for this matrix A, let's find the determinant. If I want to find A to the m, for example, we still need to find the eigenvalue and eigenvalue first. So determine A minus lambda I equals 0. Minus 2 minus lambda minus 1, and 4, 3 minus lambda. This is equal to 0. Then your characteristic equation is lambda squared minus lambda minus 2 equals 0. You can get two distinct eigenvalues, lambda 1 minus 1, lambda 2, 2. So I can change lambda to A. Matrix A squared minus 2A minus 2. Then I need to times the identity matrix equals, so this one should get a 0 matrix. So that means A squared, I can find A squared is 2 times the identity matrix plus your A. Now you can find the A cube, A to the 4th, because A cube will be this times A. So I will get 2A plus A squared. And what is A squared? A squared is 2 identity matrix plus A. So you got 2 identity matrix plus 3A. And A to the 4th, here you times A, right? And then you have A squared, replace that, then you get 6 identity matrix plus 5A. A to the 5th, you got 10 identity matrix plus 11A. And A to the 6th, 22 identity matrix plus 21A. Okay, that means 22 identity matrix 1001. And then 21A, oops, plus 21A, A is minus 2, minus 1, 4, 3. So you get minus 20, minus 21, 84, and 85. Let's generalize this, because first we found the characteristic equation, and then we changed the lambda to the matrix A. But if we see the characteristic equation again, lambda equals 2 plus lambda. This is the characteristic equation. Then lambda cube will be 2 plus 3 lambda. Lambda to the 4th will be 6 plus 5 lambda. And so on. Then I can change to A to the M will be C naught identity matrix plus C1A. And also lambda to the M is equal to C naught plus C1 lambda. Then we just need to solve C naught and C1. And remember, how do we solve that? We have lambda 1 equals minus 1, lambda 2 is 2. So we can choose we can solve C0, C1 by having lambda equals -1 and 2. So -1, first -1 to the m will be C0 plus C1 times -1. 2 to the m will be C0 plus C1 times 2. We get C0 1/3 2 to the m plus 2 to the m times 1 minus 1 to the m. And C1 and therefore we can change that to A. So A to the m will be equal to okay. So in general, A to the m will be C0 I plus C1 A, and I also have A squared to C m minus 1 A m minus 1. Where the coefficient ck depends on the value m, and k is from 0 to m minus 1. Or to m minus 1.